Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi, and today we are going to discuss about the module Optical Methods for Thickness Measurements Part 1, in which we are going to study about multiple beam interference, which is from the paper Thin Film Science and Technology. After studying this module, you should be able to understand the importance of measurement of film thickness. Secondly, you will understand about the multiple beam interference based film thickness measurement techniques. We will study in detail the study of measurement of thickness using Fizeau Fringes, which is the Tolansky Technique, and we'll study about the fringes of equal chromatic order, or we can call it in short form as FECO method, for the measurement of film thickness. Before going into the detail, let's have a brief introduction. All the films have surface thickness, and therefore when the thickness of the surface layer is of the order of the fraction of the millimeter is called thin films. The thin films may be of metallic, it is called a metallic thin film. The thin film may be of polymer, are called polymer thin film. Thin film is deposited on a smooth surface of substrate in order to get well-defined edge and a highly reflecting opaque layer. It is important to measure the thickness of thin film as the electrical, optical, and structural property the material varies drastically from the variation in thickness of the film. The most preferred technique for a specific application or process depends upon the film type, the thickness of the film, the accuracy desired, and the use of the film. The important criteria include properties such as film thickness, film transparency, film hardness, thickness uniformity, substrate smoothness, substrate optical properties, and substrate size. In many cases, there is no single best technique. The most useful techniques for determining film thickness includes multiple beam interference, ellipsometry, quartz crystal, and stylus technique. So let us now discuss the optical methods for determining the film thickness. Optical techniques for the determination of film thickness are mostly used. They are applicable to both opaque and transparent films, yielding high accuracy in thickness values measurement. In addition, measurements are quickly performed, frequently non-destructive, and utilize relatively inexpensive equipment. In the present module, multiple beam interference will be discussed in detail. So let's discuss multiple beam interference. If the interference occurs between two or more beams, the sharpness of the fringes increases markedly. This can be accomplished if the reflectivities at the two interfaces are very high, as shown in the figure 1. In figure 1, R and T represent the amplitudes of reflection and transmission. In figure 1, it can be observed that each of the two parallel glass plates has a thin, partially transparent metallic film, which is of silver, indicated by CDFE and IJLK deposited on surfaces facing each other. And another condition for multiple beam interference is small absorptivity of metal film through which light must be transmitted. In the case of multiple beam reflection, only the metal film CDFE needs to be moderately transparent with low absorptivity, whereas for multiple beam transmission, both metal films must have low absorptivities. In the given figure 1, we can see the schematic presentation of multiple beam interference between two metal films coated glass plates. Let the medium between the two glass plates has a refractive index N1 and thickness T. The angle of incidence of the radiation is theta. In the case of transmission, the intensity is given by the well-known Airy formula. Airy formula is given as I is equal to I max divided by 1 plus F into sine square beta prime by 2. Let's call it equation number 1. Beta prime is given as beta prime equals to 2 pi by lambda into 2n1t cos theta, which can be written as equal to 2 capital N into pi. Let's call this as equation number 2, where n is a positive integer. I max is equals to T upon T plus A whole square. Let's call this equation number 3. And capital F is equals to 4R divided by 1 minus R whole square. Let's call this equation number 4. R is the ratio of reflected energy to the incident energy. T is the ratio of transmitted energy to the incident energy. Phase changes occurring on reflection are not considered in equation number 2. F is the coefficient of fineness. This coefficient is a measure of sharpness of the interference fringes. With properly evaporated metal films, a reflectivity of near 0.95 is possible, which gives a value of F of over 1200. Thus, as long as sine beta prime by 2 has any significant value, the intensity of the transmitted light I is very small. That can be seen from equation number 1. If sine beta prime by 2 becomes 0, I reaches the maximum intensity of I max. This occurs only if beta prime is an integral value of 2 pi, and therefore very sharp interference fringes with intensity maxima for integral values of n are observed. In the case of multiple beam interference by reflection, the interference pattern forms interferogram, which is just the opposite of that seen in transmission, provided the absorptivity is small. In other words, where there are sharp, bright fringes on a dark background in transmission for integral values of n, observation of the reflected light gives sharp, dark fringes on a bright background. With an increase in the absorption A, the intensity of the entire transmitted pattern is decreased by T divided by T plus A whole square. In the reflected fringe system, however, an increase in the absorption A prevents the fringe minimum from going to 0. Hence, with larger A, the reflected fringes tend to diminish under the same conditions where they would still be seen on transmission. Consequently, to obtain sharply delineated reflected fringe system, the absorption A should be kept to a minimum. In addition to the requirements of high reflectivity and small absorption or good quality fringes, the distance between the plate, that is T, should be kept as small as possible. From equation 2, it can be seen that there are various factors that contribute to the development of fringes. Fringe systems are recognized according to the method of fringe formation, and two cases are distinguished in multiple beam interferometry. Fizeau fringes are generated by monochromatic light and represent contours of equal thickness arising in an area of varying thickness T between the two glass plates, similar to those shown in the figure 1. This is accomplished by contacting the two glass plates such that they form a slight wedge at an angle alpha so that T varies between the two plates. The angle alpha is generally made very small so that consecutive fringes are spaced as far apart as possible. The angle of incidence theta is typically kept near 0 degree and the medium is air. The refractive index of air, which is N1, is equals to 1. Hence, the spacing between the fringes corresponds to a thickness difference of lambda by 2, where lambda is the wavelength of the monochromatic radiation being used. You can see figure 2 in which we are able to see semi-transparent optical flat ABFE with film sample KLMI, including step LM for multiple beam interferometric measurement of film thickness. Second multiple beam interferometry technique is referred to as fringes of equal chromatic order, or in the short form FECO. In this case, white light source is made to focus at an angle of incidence of 0 degree and the reflected or transmitted white light is dispersed by a spectrograph, thus offering a means of varying wavelength lambda. According to equation 2, fringes will form for certain values of T by lambda. Then, FECO fringes can be obtained with the two metal surfaces parallel to each other, whereas the plates must be inclined relative to each other to produce Fizeau fringes. The spacing between the fringes on the interferogram or spectrum is inversely proportional to the thickness. Multiple beam interferometry for the measurement of film thickness can be implemented by the method of Donaldson and Tolansky, which is shown in figure 2. The arrangement differs from figure 1 in that the substrate GHJI supports a film KLMI whose thickness is to be measured. A highly reflective opaque metal film NKJO is evaporated on top of the film KLMI. Silver films of about 1000 Armstrong thickness are typically used for this purpose. The step LM in the original film may be formed either by etching the film after deposition or by masking the MJ part of the substrate during deposition. Evaporated silver replicates such steps accurately. The bottom surface of the reference plate ABCD has a thin, highly reflective, semi-transparent film as in figure 1. To produce Fizeau fringes, the reference plate ABCD is inclined at an angle with respect to the substrate underneath it, as shown in the figure 3. In the case of FECO fringes, the film substrate and the optical flat are parallel to each other. The distance between the plates is adjusted according to the film thickness, since the magnification, that is the spacing between the fringes on the interferogram, increases with decreasing separation between the plates. The film KLMI may be either opaque or transparent in these techniques. The requirements for the methods are that a step or a channel can be made in the film down to the substrate surface, that the substrate is fairly flat and specially smooth, that the film itself has a smooth surface for fringe formation, and that the film should not be altered by the deposition of the reflective coating. For example, some organic films are altered by the heat generated during the evaporation of the reflected metal and should not be measured by this technique. Measurement of thickness using Fizeau Fringes or Tolansky Technique. The use of Fizeau Fringes for thickness measurements is commonly called the Tolansky Technique in recognition of Tolansky's contribution to the field of multiple beam interferometry. A schematic representation of Fizeau fringes produced by multiple beam interference is shown in Figure 3. Figure 3 shows the schematic view of apparatus for producing multiple beam Fizeau fringes. The film thickness is given by D equals to delta n into lambda by 2, where delta n is the number of fringes. In the interferogram based on Tolansky technique shown in Figure 3, the depth of the channel or the film thickness is exactly 1/2 of the separation between fringes. That is, delta n is equal to 0.5, and therefore the film thickness is lambda by 4. If the wavelength were that of the green mercury line, the film thickness would be 1365 angstrom. Commercial microscopes which utilize Fizeau multiple beam interferometry are available. In addition to the conventional metallurgical microscopes, can be easily equipped with Fizeau plate attachments for interferometric measurements. These plate attachments are generally equipped with 3 adjustable screws to determine the tilt of the plate relative to the specimen and thus control the direction and spacing of the interference fringes. Accurate thickness measurements require careful evaluation of fringe fractions, which can be measured by a calibrated microscope eyepiece or photomicrograph of the fringe system. Either way, the evaluation requires a linear measurement, the accuracy of which is strongly dependent on the sharpness of the fringes. This would require the optical flat Fizeau plate to have high reflectivity and low absorptivity. 2 other prerequisites for an accurate thickness measurement are: first one is the smooth and flat film surface, and second one is the monochromatic light source. Thickness measurements from 10 nanometer to 2 micrometer can be made with an accuracy of plus minus 3 nanometer. Figure 4 shows the schematic of apparatus for producing multiple beam fringes of equal chromatic order, or FECO. You can see in the figure a collimated white line coming onto the substrate, in which it passes through half silvered mirror, and then partially transparent silver coating is also there. Let us now study about the fringes of equal chromatic order, or in short form we call it as FECO. Fringes of equal chromatic order are more difficult to obtain but yield greater accuracy than Fizeau fringes, especially if the films are very thin. Figure 4 presents the basic principle for the apparatus of FECO. Collimated white light impinges at normal incidence on the 2 parallel plates. The reflected light is then focused on the entrance slit of the spectrograph. The image of the channel in the film must be perpendicular to the entrance slit of the spectrograph. Assuming an angle of incidence of theta is equal to 0 degree, then sharp dark fringes occur for integral values of n is equal to 2t by lambda, as shown in figure 5 for 2 different plate spacing t. Figure 5a represents the interferogram for parallel plate spacing of 2 micrometer, and figure 5b represents the interferogram for the same parallel plate spacing but with the channel 1000 angstrom corresponding to film thickness of 1000 angstrom. The fringes are observed as the wavelength lambda is varied by the spectrograph and are recorded on the photographic plate corresponding to lambda equals to 2T by N. The resulting interferograms are shown schematically in figure 5, where the scale is assumed to be linear in wavelength. With a linear wavelength scale, the fringes are not equidistant on the interferogram. The order of the fringe increases with decreasing wavelength of the fringe. It is sometimes preferable to give the order as n is equal to 2 into T into V, where V is a reciprocal wavelength or the frequency in wave numbers, as this relation shows n to be linear with wave number. However, this linearity is not found to be exactly true if the phase changes at the two reflecting interfaces vary with wavelength. Hence, there may be a slight dispersion with wavelength, but the effect of phase change on the determined fringes is very small. In practical cases, the spacing between plates is not known, so a prior assumption is made as the hypothetical case shown in figure 5. It is therefore necessary to deduce T as well as N from the wavelengths of the observed fringes. Figure 5 shows firstly the interferogram for parallel plate spacing 2 mu, and in the B part it shows the interferogram for the same parallel plate spacing but with a channel 1000 angstrom corresponding to film thickness of 1000 angstrom. If N1 is the order of a fringe corresponding to wavelength lambda 1, then N1 plus 1 is the order of the next fringe with a shorter wavelength lambda naught on the interferogram. Neglecting the small phase change dispersion, we have N1 into lambda 1 equals to N1 plus 1 into lambda naught, which is equal to 2T. Let's call this equation as equation 5. Now solving for N1, we obtain N1 equals to lambda naught divided by lambda 1 minus lambda naught, which is equation number 6. And we can now express T solely in terms of measured wavelengths as T equals to N1 into lambda 1 divided by 2 equals to lambda 1 into lambda naught divided by 2 into lambda 1 minus lambda naught. This is equation number 7. To determine the film thickness, consider that a channel of depth D causes the fringe of the order N1 to be displaced to a new wavelength lambda 1. Consequently, the film thickness D must satisfy the relation T plus D equals to N1 into lambda 1 divided by 2. Let's call this as equation number 8. Thus, the film thickness D is given by subtracting equation 8 from equation 7. D is equals to N1 lambda 1 prime divided by 2 minus N1 lambda 1 divided by 2, which equals to lambda 1 prime minus lambda 1 divided by 2 into lambda naught divided by lambda 1 minus lambda naught. This is equation number 9. From the figure 5b, the fringe displacements due to the channel are clearly related to the order n of the fringes outside the channel. However, if the slope were so steep that the order in the channel could not be related to that Outside the channel, the film thickness could still be derived from the equation given below. The equation is D equals to 1 by 2 into N1 prime into lambda 1 prime minus N1 into lambda 1, whereby the unknown order N1 prime must be obtained by observation of a second displaced fringe of the order of N1 prime plus 1, as we have seen in equation number 7. Also, the magnification increases with decreasing spacing between the plates in interferogram. So students, let us summarize what we have learned in this module. In this module, we have learned the importance of film thickness. Then we explored about the multiple beam interference based film thickness measurement techniques. Secondly, we studied about measurement of thickness using Fizeau Fringes or Tolansky Technique. Then we explored fringes of equal chromatic order or the FECO method to measure the thickness of films. Thank you.